Hello everybody, this is Daniele Ciani from the National Research Council of Italy. I will present a study on the combination of altimeter-derived currents and sea surface temperature to improve the surface currents estimate provided by standard altimetry in the North Atlantic Ocean. And we will also see an intercomparison study of the OSTIA level 4 near real-time and reprocessed SSTs for this type of applications. Ocean currents are key factors regulating the properties of the ocean surface, the interaction between the ocean and the lower atmospheres, but they're also involved in many practical activities, like, for example, the optimization of ship routing. And all these applications require a very high resolution spatial temporal monitoring of the ocean surface circulation. Presently, the monitoring of the ocean surface circulation is achieved combining the geostrophic approximation, the geostrophic balance theory, in which currents are derived from observations of the ocean surface topography. And ocean surface topography is observed through constellation of nadir-looking radar altimeters, which provide observations of the estimates of the absolute dynamic topography along one-dimensional tracks, which are in the end spatially interpolated in order to get two-dimensional maps of ADT and obtain the surface circulation through the geostrophic balance. This can cause limitations in the estimate of the actual surface circulation using the geostrophic balance and the altimeter constellation, mainly due to artifacts in the optimal interpolation of the absolute dynamic topography, but also to the fact that the geostrophic flow is only representative of a large-scale, low-frequency component of the total surface currents. Limitations due to the sampling will be certainly improved thanks to the SWOT mission, which was launched in late 2022, which will provide wide swath and native to the observations of the ADT. Here we can have an example of the effects of the limitations of the altimeter system. So if we estimate the eastward velocity intensity in two moorings in the Pacific and in the Atlantic Ocean, we have in situ measured currents in blue, and in green you have the same estimate provided by the constellation of radar altimeters. And as you can see, we are losing a consistent fraction of the temporal variability of our signal. What we have been studying in the past few years in order to improve the estimates of the ocean surface circulation from satellite altimeters is to extract and combine the satellite altimetry information with additional native two-dimensional satellite images, like, for instance, sea surface temperature, so independently observed tracers that contain, as in this nice example provided by the Sentinel-3 SLSTR sensor, lots of signature on the mesoscale and sub-mesoscale activity, as you can see from the meanders and eddies in this example in the North Atlantic Ocean. We go on with the presentation of the methodologies and data employed in our study. So our methodology basically relies on the SST evolution equation highlighted on the top of this slide, which accounts for the SST spatial and temporal variation, as well as on the source and sink terms, and to invert this equation in order to get information on the zonal and meridional flow, here indicated as U and V. So in particular, in this exercise, we consider the altimeter-derived currents as a first-guess background estimate of the surface circulation, while sea surface temperature is used to build correction factors to this initial background estimate of the surface currents. So what we get in the end is a set of equations that you see on your left, in which you can recognize the background currents provided by altimetry for each of the two components, and the correction factors provided by SST, mainly built from the knowledge of the SST gradients in space and time. In 2020, with colleagues from CNR, CLS and the European Space Agency, we performed an intercomparison study for global scale applications, accounting for three GHRSST level 4 SST products, namely the Muir SST, which yielded the best results in terms of the representation of high-resolution frontal features, although their use is mainly recommended for cloud-free areas. The RAMs merged microwave plus infrared SST were characterized by good spatial homogeneity, and they were particularly recommended for low to mid-latitude surface currents reconstruction. And in the end, the OSTIA SSTs provided, let's say, the best trade-off for the global scale applications, as they were characterized by good spatial homogeneity, also good performances for low to mid-latitude applications, but also mitigated some of the degradations that we found in polar areas with the other datasets. But in the end, none of the considered sea surface temperature yielded ubiquitous improvements of the altimeter-derived current. So degradation could appear, and they made really challenging their global scale application, especially in the perspective of an operational service. But also interestingly, this study revealed that somehow this technique can be considered as a tool for indirect SST validation, mainly for ocean dynamics studies. We here present a regional application in one of the key areas of the world ocean, the North Atlantic, in which we merged altimeter-derived geostrophic currents, the DUAX-18 version, with the level 4 OSTIA SSTs, in order to get a 10 years long time series of ocean surface currents at nominal 1/10 of a degree spatial resolution and daily temporal resolution. These activities were part of the ESA funded World Ocean Circulation Project, but also benefited from interactions with the GHRSST task team on climatology and level 4 intercomparison. We thus go on with the presentation of our main results. Here on a test case on the 24th of March 2015, you can have an example of the sea surface temperature correction along intense sea surface temperature gradients, which are mainly resulting in a rotation of the surface currents vectors, so larger correction in large SST gradient areas, while as you can see, the surface circulation is basically the one provided by satellite altimetry in low sea surface temperature gradient areas. In this additional example that you can visualize through the website provided at the bottom of the slide, you can see on July 11, 2018, a quite sharp SST frontal feature captured by the Sentinel-3 SLSTR sensor, and an intercomparison of three surface currents estimates. In white, you have the, so emphasized by the white arrow, the flow given by the altimeter system. In blue, the one given by the WOC and ATL2D dataset. So the one we are computing considering the combination of altimetry and SST. And in green, you can see the evolution of a surface drifter on the same date. And you can see that considering the combination of altimetry and SST yields a surface flow which is much more in agreement with in situ observations. The test case that we showed previously was just probably a lucky case, so we double checked for statistics on a much longer time period. So in this case, we consider 3 years from 2014 to 2016. We performed an intercomparison of our of our ocean surface currents reconstruction with respect to standard altimetry, using in situ measured currents intensities as a benchmark. And the evaluation of the improvement was computed through the improvement index, which is provided bottom left in this slide. So here in the figures, you can visualize lots of red and blue areas, which respectively represent an improvement or a degradation with respect to the standard altimeter system as a percentage. So you can see that considering the OSTIA near real-time product, we can get an overall improvement of the surface currents in the North Atlantic Ocean, in which again the main corrections are visible in the strongest SST gradient areas, so along the axis of the Gulf Stream, but occasionally some degradations are found. And very interestingly, the strongest degradation almost disappear when we consider the OSTIA reprocessed product. So based on the previous results, we decided to take a closer look at the OSTIA near real-time and reprocessed datasets. And in particular, we performed a visual inspection of randomly selected test cases along the entire time series. In particular, here I'm referring to the time series which are available through the Copernicus website, and I reported the Copernicus dataset IDs and file names at the bottom of this slide. There were some unlucky cases, like the one presented by the three panels on the top on March 2015, in which indeed the representation of the main mesoscale features by the near real-time and reprocessed product is significantly different. So if we intercompare these two SST estimates, we can get differences up to 10 degrees. And other cases in which the near real-time and reprocessed product look at least qualitatively very similar, and both of them provide a quite good description of the main mesoscale activity in the North Atlantic, although differences up to 5 degrees can be obtained, probably mainly due to a shift of the dynamical features along the axis of the Gulf Stream. As an additional exercise, we randomly selected the year 2016 and we intercompared firstly the temporal standard deviation of the reprocessed and near real-time SSTs. As you can see, the reprocessed dataset is characterized by a larger temporal standard deviation in dynamically active areas, so mainly along the axis of the Gulf Stream, but also on a subset of the North Atlantic area, emphasized by the green box. We performed the spectral analysis of the SST fields, near real-time and reprocessed again. And as you can see by the red line, the red spectrum, it seems that the reprocessed OSTIAs contain much more spectral energy in the, let's say, large mesoscale to submesoscale range. So roughly from a few hundreds of kilometers up to a few tens of kilometers. The WOC and ATL to the product was thus based on the OSTIA reprocessed SSTs and yielded the improvements with respect to standard altimetry that you can see here top left on this slide, as done previously for the 3 years long reconstruction, but this time on a 10 years long basis. Concluding, we produced a 10 years long time series of surface currents in the North Atlantic, correcting the altimeter-derived geostrophic currents via SST. This yielded correction mainly in large SST gradient areas, which were quantified up to about 15% with respect to the altimeter-derived system, and our intercomparison of the OSTIA REP and NRT products suggested the use of the REP products for our dynamical application, so mainly suggesting this dataset for the reprocessing of past altimeter data. Thank you so much for your attention.